Hi, everyone. In this lesson, we will learn detection and evaluation of concrete carbonation depth. Now, please look at the chemical formula on the screen. Does it sound familiar? This is what we learned in inorganic chemistry. The carbonation reaction of slate lime. Before the reaction, calcium hydroxide is alkaline. The calcium carbonate generated after the reaction is neutral. Then, how do we determine? Has this chemical reaction occurred? In daily life, we can use pH test paper to detect the acidity or alkalinity of the solution. The pH color comparison chart is divided into 14 levels. The smaller the number, the stronger the acidity. The higher the number, the stronger the alkaline. Judgment of acidity and alkalinity for solid objects. We can prepare the corresponding acid-base indicator. Commonly used solutions include colorless phenolphthalein, purple litmus reagent, etc. This task mainly explains the following four contents. 1. Mechanism of concrete carbonation. 2. Method for detecting carbonation depth. 3. Steps for carbonation depth detection. 4. Evaluation of carbonation depth inspection results. Domestic and foreign scholars have conducted extensive experimental research and theoretical analysis. Summarized that the main cause of concrete carbonation is alkaline substances present in concrete. For example, calcium hydroxide comes into contact with carbon dioxide in the air, resulting in neutralization reaction. Generated chemical substances, such as carbonate, altered the composition of the concrete. We conducted a comparative test. Drop colorless phenolphthalein reagent into the neutral and alkaline solutions to observe its changes. By observing in an alkaline solution, the phenolphthalein reagent quickly turns purple-red. Therefore, the inspection of concrete carbonation condition, typically used in concrete. Spray acid-base indicator on the fresh cross-section. By observing the color change of the acid-base indicator to determine concrete carbonation depth. We perform the concrete carbonation detection in 4 steps. Step 1. Arrangement of measurement areas and test holes. First, the measurement area should include areas with representative corrosion potential measurement results, while also reflecting different conditions and locations with varying concrete quality. Measurement areas should be arranged on the outer surface of the structure. Second, the number of measurement areas should not be fewer than 3. Measurement areas shall be uniformly arranged. Each measurement area should have 3 test holes arranged in a triangular pattern. The hole spacing should be greater than twice the hole diameter. In the end, the distance of the test hole from the component edge should greater than 2.5 times the cover thickness. Step 2. Form a test hole. Using an impact drill with a 20 mm diameter drill bit, drill holes at the measuring point locations. After forming the hole, use a round brush to remove debris from the hole. Clean the powder thoroughly. Uniformly number the test holes in the measurement areas and draw a schematic diagram. Step 3. Measurement of carbonation depth. First, before testing, use a 75% alcohol solution. Configure with white phenolphthalein powder to form phenolphthalein solvent with a concentration of 1% to 3%. Load into a sprayer for standby use. The solvent should be a colorless, transparent liquid. Second, spray phenolphthalein indicator onto the test hole wall. After the phenolphthalein indicator changes color, measure the concrete surface with a depth caliper. Measure the depth from concrete surface to the color change boundary with a depth caliper, accurate to 0.25 mm. The phenolphthalein indicator changes from colorless to purple. The concrete is not carbonated. Where the phenolphthalein indicator does not change color, the concrete has carbonated. Step 4. Data sorting. Mark the measurement results on the measurement area. On the test hole arrangement diagram, sort the measured values into a list. On-site readings are accurate to 0.25 mm. The calculated value is accurate to 0.5 mm. Concrete carbonation depth. Evaluation of the impact on reinforcement corrosion. The ratio Kc can be taken as the average carbonation depth of the component divided by the average protective layer thickness of such components. And consider its dispersion condition. Evaluate individual components according to the values in the table. If Kc is less than 0.5, evaluation scale is 1. Through the learning of key points in this task, it is hoped that you can describe the main mechanism of concrete carbonation, independently complete the concrete carbonation depth measurement operation, following the numerical rounding principle, correctly record and calculate the concrete carbonation depth value, and result evaluation. Also, during our operation process, pay close attention to the test process and results. Carefully record. Will diligently study. Keep a meticulous work attitude in mind. Only then can one handle future work with ease.